Hi, everybody. Welcome back to Dave's Math Channel. My name is David Tear. Today I'm going to talk about a very important topic in math, namely the topic of prime numbers. I'm sure most of you have heard of them, and you probably know what they are. I'll just go through the definition really quickly. A prime number is a positive integer with two factors, one in itself. Some people think one's prime. It's not. One is a special number, it's called a unit. But other than one, every other positive integer is either prime or composite. And all composite means is that you can factor it into a product of primes. It has more than two factors. So that's primes. Uh, and here's a short list of this is all the primes up to 100. And as you can see, there's 25 of them. And you might wonder in general how to generate primes. There's actually a very famous method. This was actually discovered by a guy, a Greek from 200 BC. It's called the sieve of Eratosthenes. Um, so anyway, what you do, the way you find primes, I think I have a short video on this. I'm not going to go into this detail, but you start with two. Everybody knows that's prime. And then once you get two, you cross out every multiple of two greater than two. So you do that first, and then you look at to see what the next remaining number is, and that happens to be three. So then you do the same thing. You cross out all multiples of three, including 9, 15, 21. And when you're done with that, the next number on your list that hasn't been crossed out is 5. So 5 is prime, and then you cross out all the multiples of 5, everybody on this column. And then when you're done with that, there's 7 remaining. So now you cross out all the multiples of 7. You might think you have to go all the way to 100. You don't. You can stop at 10. It turns out in general, if you want to find all the primes up to some limit n, you only have to go up to the square root of n. So the numbers in yellow, these are all the numbers that are remaining after we did all this. These are all the primes up to 100. Kind of a neat method. And believe it or not, this is still the most efficient method known for generating all the primes up to a limit. Pretty amazing. Uh, Anyway, why do we care about primes? Well, there's a lot of reasons. I think one of the biggest reasons we care about primes is there's something called the unique factorization of integers theorem, also known as the fundamental theorem of arithmetic. And what this theorem basically says is that every number, every positive integer n, has a unique factorization into the product of prime numbers, if we don't care about the order. So every number n has a unique expression like this. P1 is its first prime factor. That's raised to power E1, some exponent, P2 to the E2, P3 to the E3, so on, up to the last prime, the biggest prime factor, PK to the EK. So pretty remarkable. And so you can kind of think of primes as the building blocks of the integers, of the positive integers, because there's a unique factorization of every integer into primes. And there's a nice way you can get the prime factorization. And probably most of you learned this in grade school. These are called factor trees. And what you do to make a factor tree, look at the one on the left, you just pick two factors of the number you start with, in this case 144. So 144 is 72 times 2. 2 happens to be prime, you circle it. But then 72 is still composite, so you write that as a product of two other factors, 9 and 8. And neither of those are prime, so you have to factor both of those. 9 is 3 times 3. 3 is prime, so you're done with 9. 8 is 2 times 2 times 2. You're done with 8. And everything, these are called leaves, the numbers that are circled. So all the leaves are the prime factors of 144. So it's four factors of 2, so you can write that as 2 to the 4th power. And then you got two factors of 3, that's 3 squared. So the answer is 2 to the 4th times 3 squared. And then you could do it another way. Here's another way to factor 144. 12 times 12 on the right. 12 is 4 times 3. You can do that twice. 3 is prime, 4 isn't. So you have to factor 4. 4 is 2 times 2. And when you're done with all this, you're with the same prime factors. 4 factors of 2 and 2 factors of 3. 2 to the 4th times 3 squared. That's a unique prime factorization of 144. Kind of neat, I think. And so another interesting fact about primes, this isn't very obvious, but it turns out that there are infinitely many prime numbers. They do tend to get rarer as the numbers get bigger, but not very fast, as I'll explain later. But here's a proof. You can prove by contradiction. So suppose you have a complete list of all the primes, P1 up to PK. Now, here's the trick. add 1 to that product. So you define the number A, which is the product of K primes, add 1. A is obviously bigger than any number on the list, so we assume that these are all the primes, so A has to be composite. Uh, and by the unique factorization theorem, or the fundamental theorem of arithmetic, we know since A is composite, it has a prime divisor. So there's some prime Pj that divides A, but then we get a contradiction because if we take the remainder after we divide the product by Pj plus 1 by Ej, you get a 1 is its remainder. You do that for any prime factor of A will give you a remainder of 1. And that means that Pj cannot be a prime factor of A. So that's our proof. We get a contradiction. Nice proof. And Euclid proved this around 300 BC. This was even before Eratosthenes. Pretty remarkable. And those Greeks knew their stuff. But there's other interesting properties of primes. There's a lot of conjectures about primes. Primes are pretty mysterious. They don't seem to follow any nice pattern. They seem to be kind of random. But this guy named Goldbach, he was a Belgian amateur mathematician in the late 17th century. He came up with a conjecture known as Goldbach's conjecture, which is still unproven, but it seems to be true. He conjectured that every even number greater than 2 could be written as a sum of 2 primes, possibly equal. And you can check that yourself. This graph kind of does that. So all the numbers in the middle of this graph are even numbers, and if you go on the blue lines, you get 1 prime factor, and you go on the red line, you get another prime factor. And you don't have to start in the center. You can start anywhere on these horizontal gray lines. So that shows you all the ways you can represent every even number greater than 4 as the sum of 2 primes. And this has been checked up to something like 4 times 10 to the 18th, a very huge number, but nobody's been able to prove it. And there's a lot of other facts about primes that seem obvious, but nobody's been able to prove. But here's a theorem, another nice theorem. This was a very hard theorem to prove, by the way. It's called the prime number theorem. It was conjectured, I believe, in 1796, and it took 100 years to prove this. It wasn't proven until 1896. But basically, what this formula is an asymptotic formula for how many primes there are up to a given limit. This function pi of x is the number of primes up to x. X is some positive real number. So it just counts how many primes there are up to x. And it says that pi of x is asymptotic to x over natural logarithm of x. And that was proven. And you can even look at tables that kind of verify this. The numbers on the left, the numbers on the far left are the limit. This is n. This is the number, and then the next column has pi of n, the number of primes up to n. It grows, but it grows like n over log n. And you can look at these ratios. I mean, on that third column is pi of n over n. It does get smaller as n gets larger. This is kind of the density of primes up to n. So there's 1/4 of all the numbers up to 100 are prime. But by the time you get to 10 to the 14th, only about 3% of the numbers up to 10 to the 14th are prime. And you can calculate 1 over log n, and it does approach the numbers on the right column, the fourth column, do approach the numbers in the third column. That's what the prime number theorem says. Pretty remarkable. So anyway, that's just a useful fact about primes. And there's other kind of weird facts about primes. They seem to be kind of random, but there was a guy named Stanislaw Ulam, a very famous number theorist in the 1950s. He got bored one day. He was at a lecture. He wasn't interested in the lecture, so he started doodling. He started playing around with prime numbers. So he just thought for fun he'd write down the prime numbers on a square spiral going out. So the first prime is 2. That would be the second number on the spiral, then 3, then 5, 7, so on. But much to his surprise, when he did this, he found that the primes tend to lie on diagonal lines. And he didn't have a good explanation for that. It was pretty remarkable, discovery, kind of unexpected discovery. Here's a bigger picture, and you can kind of see diagonal line patterns. So kind of interesting. What that really means is that primes tend to congregate along quadratic sequences. And you don't have to use a square. You can use a hexagon. You get patterns on a hexagon, too. So kind of a remarkable. I don't think anybody's proven why this happens, but it's just kind of a remarkable fact about primes. And finally, one more thing I want to mention. The RSA crypto system. Maybe you guys have heard of this. So you might wonder, are there any practical uses for primes? For a long time, there really weren't. But now, thank yourself for primes, because primes allow us to use secret information on the web, like your passwords and your bank account information. The way that works is, this is what's called the RSA crypto system. Suppose Alice wants to send a message to Bob across a noisy and insecure channel where other people might be listening to the conversation. How does she do it? How does she have a private conversation with Bob and make sure nobody else is listening in on her? Well, the way you do that is you do this thing called the RSA crypto system. This could be a whole nother video. I don't want to describe the whole procedure, but basically, it's Bob comes up with a public key, and Alice comes up with a private key that she only shares with Bob. Nobody on the network can possibly determine Alice's private key, Bob's private key that Alice gives him, because in order to break this code, you would have to factor a product of two really, really large prime numbers. The way they do it today, they usually use prime numbers with about 150 digits each, and they multiply them together. And an interesting thing about factoring's hard. It's hard to factor large numbers, but it's much easier to test whether numbers about that size are prime and then multiply them together. So it's easy to encode, but it's almost impossible to decode. As a matter of fact, it would take the best classical computers we have today longer than the age of the universe to break RSA. So RSA is secure, at least for now. Quantum computers might be able to break it, but at least for now, we're safe with RSA. And that's a very important practical application of prime numbers. And that concludes my lecture for tonight on prime numbers. I hope you enjoyed it, and I'll see you next time.